Hello, welcome. And today I'm going to be talking about time and the idea of time. Before we get too deep into the premise of this talk, we got to lay some ground rules or some ideas for you to understand the concept of how time works. The first is space-time continuum. Space-time continuum is just a fancy way to say the universe, because the universe is a coupled phenomenon between space and time. The basic equation for time is distance over speed. We all know the speed equation is just distance over time. Manipulate that, you get time is equal to distance over speed. That means we can't have space without time. We can't have time without space. Before there was the universe, there was no space, there was no stuff, there was no time because there was nothing. And then vice versa, you can't have stuff, you can't have things and time not be a part of the equation. The next thing we have to understand is that time is linear. By linear, I just mean that it moves in a straight line. It's one series of events after another in chronological order or in a specific order. And when it moves in that one direction, it keeps moving in that direction. So time doesn't stop. You can't stop time. You can't just freeze reality. Time just keeps on moving, and we can't revert time or backtrack events. If you drop a plate or a coffee mug and it shatters, you can't reverse that. You can't reverse that event back before the event happened. The event happened. You might be able to get the mug back to unshattered, or you might be able to repair the mug or get the mug back to its condition before you dropped it, but you can't revert that event that happened. And that's the idea that time is linear. So now we're going to get to the modern view of like 1 second, which is the basic measurement we have of time. How many seconds, or a minute is just a group of seconds. 60 counts. A second is a count. 60 counts is labeled as a minute, and then 60 minutes, which is 60 counts, is an hour, so forth and so forth to days, years. But what is our second? Our modern day view is just 1/60th of a minute. It's just you take 1 second, 60 of those, you get a minute. Well, the true definition of 1 second is the duration of 9,192,631,770 period or oscillations between two hyperfine levels of the ground state of cesium-133 atom. Let me backtrack and unpack that for you. So 1 second, so if you take the element cesium, it's an element in the periodic table of elements, and cesium-133, and if you were to measure how many times between there, so these two hyperfine lines of the ground state, don't worry about that, but just know that this atom vibrates. It's vibrating. And each period or oscillations between these hyperfine levels. Just think of it as you have a level here on the left, a level on the right, and it's bouncing back and forth between those two levels. Like you're running up and down a basketball court. 1 second is how long it takes for this atom to vibrate 9.1 billion times between these two levels. So it's vibrating extremely fast, but that's how long it takes to make 9.1 billion vibrations. Takes 1 second. That's the true literal definition of 1 second. That's how you're able to actually physically quantify 1 second. Now, that's just the idea of time. Now we're going to get deeper into the physics of it. But first, we have to understand that time is relative. That's a very cliche or very common thing that's said, but I feel like it gets thrown around a lot. So we have to understand, what do people mean, especially like what do scientists mean when they say time is relative? It sounds super fancy, makes you sound smart when you're talking to somebody, say, oh, time is relative. What does that mean? We have to understand inertial reference frames, because time is relative to your reference frame. So when somebody's making an observation, or whether it's observation of time, distance, whatever it is, observations that can be taken inside a reference frame or outside a reference frame. If you're measuring a collision in a car, the car is the inertial reference frame. If you're outside of that, then you're outside that reference frame. Does that make sense? So if you're in a drag race and you're in the passenger seat of the drag race, you're inside the inertial reference frame, making observations or doing measurements, whatever the experiment is. But if, let's say you're in the stands and you're clocking in the car and yourself, you're outside the inertial reference frame. Or you're in your own reference frame. You can have your own reference frame, but the inertial reference frame, the frame that the frame of the target observation, you're outside that reference frame. So that's what time is relative means, that time is relative to a respected reference frame. And we're going to get to some examples of that in a few slides. Now I want to go over time dilation because that's where time gets interesting. And that's what people really get excited about, is when time does weird things. On Earth, things aren't moving around fast enough for us to experience crazy amounts of time dilation. But the main thing with time dilation is just speed. So I have an equation for people listening. The equation is delta t is equal to delta t naught over square root of 1 minus v squared over c squared. This looks complicated, but it's really not. But first, we got to understand what proper time is. So proper time is time measured by a clock that has the same motion as the observer. So you have two different proper times. We'll use an example of somebody in a spaceship, like an astronaut, because we have an example of that later. The astronaut has his own clock, his or her own clock. And then whoever's observing the astronaut on Earth has their own clock. The clock on the spaceship with the astronaut is the astronaut's proper time. The clock on Earth with the observer on Earth, that's the Earth observer's proper time. So delta t means the difference in those two. So you take the difference of the proper time of the astronaut and the proper time of the Earth observer, and that's how you get t naught. And then all you do is just divide that by 1 minus v squared. That's the velocity of the rocket ship, because the person on Earth is measuring the time for the astronaut in the spaceship. So you take the velocity of the spaceship, however fast it's traveling, square, divide that by the speed of light, which is 3 times 10 to the 8 meters per second. And then you take 1 minus that number. That's how you get time dilation. Your delta t will give you how much time has been dilated. So that's how it's calculated with an equation. There's also another way time can be dilated with, traveling close to the speed of light, as well as gravity. So now we're going back into the concept of the space-time continuum. Think of the space-time continuum as a trampoline. How heavy an object is will dictate how much the space-time continuum gets warped. So if you take a ping pong ball and put it on a trampoline, the trampoline's gonna sink a little bit, but not too much. Or if you take a cue ball and you put it on a trampoline, it'll sink more than the ping pong ball, but it's still not much. Now, if you take a bowling ball, a 20-pound bowling ball, trampolines can have some significant sink to it. Or if you take a decently sized boulder and place on the trampoline, now you have massive sink in the trampoline, and the trampoline represents the space-time continuum. So once you start warping space around an object with heavy gravity or heavy mass, then not only does the space get warped, but it inherently then warps time. For people watching, I have diagrams of the sun, white dwarf, neutron star, and things like the black holes, which are one of the most destructive, mysterious, most time warping objects in our universe. But you can see how it's so heavily densed on this very fine point to where it really, really warps space and time. So then it gets into some interesting phenomenon that happens, because the closer you get to the center of gravity, the slower time passes. So that's why the closer you get to a black hole, I don't know if you guys seen Interstellar, where they go on this planet that's close to a black hole. And on the planet, they only experience like 30 minutes, I believe, or maybe 40 minutes. But on this back on the spaceship, 27 years had went by, or something crazy like that, because they were closer to the black hole on the planet than they were from the spaceship. So the time moved even slower on the planet than it did out in the spaceship. That's a prime example of how this works, because they're closer to the center of gravity of the black hole. And so because of that, we actually can experience this on Earth, but since the distances are so small, the effect is so small. So on Earth, if you're actually standing up, time passes faster for your face than it does for your feet, because your feet are closer to the center of gravity than your face. And depending on how tall you are, there's a bigger discrepancy, or there's a bigger difference that you feel from your face to your feet. If you're shorter, the difference is smaller. If you're taller, the distance is bigger. So at the top of Mount Everest, a year is about 15 microseconds shorter than it is at sea level. So it is a difference in time that's experienced if you lived on Mount Everest versus sea level. But again, the distances are so small, 15 microseconds shorter, it's basically negligible because it's such a small difference. Now, getting into big differences for time dilation is the twin paradox. I love talking about the twin paradox because it's something that's fascinating with how time and the space-time continuum works. Let's say we have a pair of twins that are both age 30. Obviously, they're a pair of twins. And one twin's an astronaut, and the other one is not an astronaut, but they live on Earth, and they're going to observe their brother or sister going into space because they're really supportive. Let's say the astronaut twin is going to fly to Sirius, which is, I believe, the 5th closest star to our solar system. And they're going to travel at 99% of the speed of light. 99% of the speed of light is approximately 184,000 miles per second. Just to kind of put conception in your head how fast this astronaut's going to be moving. And that's not miles per hour, miles per second, 184,000 miles per second. So for the astronaut, the trip's going to take 2.5 years to get there and back. That's how long it's going to take for the astronaut on the rocket ship, spaceship, whatever you want to call it. And their inertial reference frame, the time that they're going to experience is 2.5 years. When the astronaut twin comes back on Earth, 17 years would have passed. So after the end of this voyage, the twin that stayed on Earth will be 47. The astronaut twin will be 32. And the reason why this is so fascinating is because if you Google how far away Sirius is from Earth, it's about 8-ish light years, 8 point something light years away. So that means if you're traveling at the speed of light, it takes a year to get there. So if you're on Earth and somebody travels, we're 99%. So we can basically say at the speed of light for sake of math, it takes them 8 years to get there. Let's say they do very quick observations. They come right back, another 8 point whatever. So we round up to 17 years have passed on Earth. Now, the reason why it didn't take 17 years for the astronaut is because speed contracts length. So when you contract length, you're going to take less time if you're in that inertial reference frame. Again, time is relative. So relative to the person traveling very close to the speed of light, length gets contracted. You can Google, there's an equation for it. But basically, the closer you get to the speed of light, the shorter distance gets contracted. So the person traveling to Sirius, that distance actually gets warped. Again, just like with gravity, going that speed, that distance gets warped down shorter to where it only takes them 1.25 years to get there, and it only takes them 1.25 years to get back. And so that's why the time is different for the observer on Earth and the observer that's in the rocket ship. And again, the speed contracts length, smaller time variable, but that's only for the astronaut's inertial reference frame. So it's relative to that astronaut. I hope that was cool. I hope that was some interesting stuff. I hope you learned something. And class is dismissed, but tell me what you guys think. I appreciate feedback. And that is all. So, yeah.